Okay, now the second part in terms of internal energy, enthalpy, and also specific heat relation. So previously we already discussed internal energy, enthalpy, and also the specific heat relationship for the ideal gas. So now we want to discuss about the internal energy, enthalpy, and also specific heat relationship for solid and also liquid. Okay, for solid and liquid actually is considered as incompressible substance where no volume change, although we apply certain force or certain pressure to the substance. But the volume change we can consider as very small, and we can ignore. Okay, so solid and liquid we consider as incompressible substance. So in terms of specific heat value, so we don't have two different value of Cp and also Cv for solid and also liquid. So we only have one term for specific heat for solid and liquid where we have only C. So we don't have specific heat at constant pressure or specific heat at constant volume. Okay, so we only have one value of specific heat for the solid and also for the liquid. Okay, in terms of internal energy with specific heat for the solid and so liquid. Okay, so now let's say we implement the energy balance equation for the specific system. So we'll get Q in equal to delta U, especially for the system not involved with moving boundary. Okay, as same as let's say we just take this schematic diagram for the specific heat at constant volume condition. So we'll have Q in equal to delta U, also equal to du equal to Ct dt. So explanation, in terms of explanation we already discussed before this. And for various specific heat with temperature condition with the integration, by using the integration, so you'll get delta U equal to U2 minus U1 equal to integration of Ct dt. Okay, so now we don't have any Cp or Cv, so we use only one value of C, specific heat. So for constant average specific heat with temperature, we will have U2 minus U1 equal to C average multiplied by T2 minus T1. Okay, next in terms of enthalpy with specific heat, so we need to consider enthalpy equation where we know that enthalpy equation H equal to U plus PV, and if we consider very small element, a very small portion of enthalpy, so we have dH equal to du plus V dP, and we need to make integration, so we'll have delta H equal to delta U plus V delta P. Okay, so substitute the value of delta U with C average delta T, a relationship between the specific heat and also the internal energy. So we'll get delta H equal to C average delta T plus V delta P. And let's say if we consider the compressed liquid, for the compressed liquid condition at low temperature and also low pressure, so we'll have this relationship where enthalpy for the compressed liquid at specific pressure and also temperature more or less equal to HF at specific temperature plus VF at specific temperature multiplied by P minus P saturated at specific temperature. So the value of HF, VF, and also P saturated for the compressed liquid we can obtain from the saturated table, refer to the specific different type of substance. However, for the compressed liquid at very high temperature and also pressure, we can assume that the value of H at certain pressure and also certain temperature equal to HF at specific temperature. So the value of HF, so you need to refer to the saturated table based on temperature. Actually same goes to the low temperature and also low pressure. The value of HF, VF, and also P saturated, the value must be referred to the saturated table based on temperature. So this is the relationship in terms of internal energy, enthalpy, and also specific heat for solid and also for the liquid. Example 3.10, the example for the specific heat involved is what I call liquid. Okay, determine the enthalpy of liquid water at 100 degrees Celsius and 15 megapascal. A, by using the compressed liquid table. B, by approximating it as a saturated liquid, and C, by using the correction equation. Okay, data, in terms of data, we have substance, water, the temperature is 100 degrees Celsius and the pressure is 15 megapascal. And A, we try to answer the first question, question A, where we need to determine the enthalpy of liquid water by using the compressed liquid table. So first, determine the water phase by using saturated water table based on pressure. Okay, we have here the saturated water table based on pressure. So we have pressure 50 megapascal, and we get the value of T saturated at 50 megapascal by using the saturated water table based on pressure, where the value of T saturated is equal to 342.24 degrees Celsius. And then compare with the temperature given, which is 100 degrees Celsius. So the value of temperature for this condition is lower than T saturated at 50 megapascal. So the phase confirmed is a compressed liquid phase. And then we need to refer to the compressed liquid table for 15 megapascal. So you need to find the table for 50 megapascal for the compressed liquid water. So at 100 degrees Celsius, okay, at 100 degrees Celsius, the value of H equal to 430.4 kilojoule per kg. So this is what I call the answer in terms of enthalpy by using the first approach, by using the compressed liquid table. Okay, next, by using the second approach, where we need to approximating the condition as a saturated liquid. So as usual, determine the water phase by saturated water table. So now we need to make assumption as required by the question. So we assume that the condition in terms of phase of the water is as saturated liquid. So we need to refer to the saturated water table based on temperature. When we make assumption, so we need to refer to the saturated water table based on temperature. So this is the table. So the pressure is 50 megapascal and the temperature is 100 degrees Celsius. So now, because we assume the phase is saturated liquid, so now the value of H is equal to HF at temperature of 100 degrees Celsius. So from the table directly we can obtain the value of H equal to 419.04 kilojoule per kg. Done for approach number 2. And then approach number 3, question C. So we need to determine the enthalpy by using the correction equation. So the correction equation is referred to this equation, where H at specific pressure and also temperature more or less equal to HF at temperature plus VF at temperature multiplied by P, pressure given, minus P saturated at specific temperature. So for the data inside this equation, so we need to use the saturated water table based on temperature. So the temperature is 100 degrees Celsius, so we can use the same table as in question B. So refer to the saturated water table based on temperature to obtain the data for the equation. So HF at 15 megapascal and also 100 degrees Celsius more or less equal to HF at 100 degrees Celsius plus VF at 100 degrees Celsius multiplied by P minus P saturated at 100 degrees Celsius. Okay, so based on the table, so we'll get HF at 100 equal to 419.04, HF at 100 degrees Celsius equal to 0.001044, and P saturated at 100 degrees Celsius equal to 101.35. Substitute into the equation, so we'll get H, the value of enthalpy by using the correction equation, is equal to 434.59. Example 3.11, long cylindrical aluminium with density rho equal to 2700 kg per meter cubic and specific heat Cp equal to 0.973 kilojoule per kilogram Kelvin of 5 cm diameter are heat treated from 20 degrees Celsius to an average temperature of 400 degrees Celsius by drawing them at a velocity of 8 meter per minute through a long oven. Determine the rate of heat transfer to the rods in the oven. Okay, based on the data given, and draw the schematic diagram. So we have an oven and also an aluminium. So we choose a part of the aluminium as our boundary. So we have Q in and the rate of what we call the speed of the aluminum rod enter the what we call come out or enter the oven is 8 meter per minute. Okay, so its substance refer to the what we call solid aluminium. Density of the aluminium 2700 kilogram per meter cubic. Specific heat of the aluminium at constant pressure equal to 0.973 kilojoule per kg Kelvin. Velocity of the rod equal to 8 meter per minute. Diameter equal to 5 cm or 0.05 meter. T initial equal to T1 equal to 20 degrees Celsius, and T final equal to T2 equal to 400 degrees Celsius. And length of the what I call of the rod that involved is, if we based on the velocity, is equal to 8 meter in 1 minute. Okay, now we analyze by using energy balance equation. So we have full energy balance equation as shown in the slide. Okay, so try to simplify the equation. So no Q out, no W in, no W out, no E mass in, no E mass out, no kinetic energy, no potential energy. So the remaining term only Q in equal to delta U. Okay, so if you elaborate the equation, so Q in equal to M multiplied by U2 minus U1, and we can replace what I call the term of U2 minus U1 with the formula involved with specific heat. Q in equal to mass multiplied by C average for the aluminium multiplied by T2 minus T1. So mass rate, because we want to determine the rate of heat transfer to the rod in the oven, so we need to determine the mass rate. So mass rate M dot equal to rho V dot, and if we refer to the what we call the diameter of the rod, so we can determine the volume, where the volume for the what we call for the rod involved is pi d square divided by 4, and now involved with rate, so we need to multiply with L over T. Okay, so we have here rho equal to pi d square by 4 multiplied by V, the velocity that involved in this system, and substitute whatever substitute all the data that we have, and we need to change in terms of time. So the time involved is 1 minute, so you need to change it to seconds, 60 minutes. So that's why you have here 2700 multiplied by pi multiplied by 0.05 square by 4 multiplied by 8 divided by 60. So we'll have in terms of mass rate equal to 0.7068 kilogram per second. For heat transfer rate, so now instead of we just use the formula for Q, so now we need to use Q in dot, where Q in dot equal to M dot multiplied by C average multiplied by T2 minus T1. So just substitute all the value that you have in terms of mass rate, C average, which is also equal to Cp that given in the equation, multiplied by temperature difference, 400 minus 20. So we'll get heat transfer rate for this problem, Q in dot equal to 261.33 kilojoule per second or kilowatt. Okay, I think that's all for chapter number 3. So I hope you understand the content of this chapter. So make sure you go through the video, all the video, and try to ask me during the live session. Okay, that's all. Assalamualaikum.